Hi everyone. Today I'm going to give a brief overview about channel analysis and comparison of channel estimation algorithms in OFDM systems, which is my final project as a part of wireless communication systems course. So we'll go through the PPT now. So this is the basic outline of the project and the presentation. The introduction to OFDM system, what exactly an OFDM system is and how it behaves, and the OFDM system architecture, the various blocks in OFDM system which are interlinked and how exactly it works, and the need for the channel estimation in OFDM system, why exactly channel estimation is required in OFDM system, and what are the parameters to be considered for channel estimation, and then the channel estimation algorithms in OFDM system. There are many channel estimation algorithms which are present, and out of which one is better, or how exactly do we implement the channel estimation algorithm, and we see the results in the simulation results through MATLAB code and implementation, and then we see the trade-offs between the various channel estimation algorithms and the performance evaluation of the various algorithms in the OFDM system. So the introduction to OFDM system. So orthogonal frequency division multiplexing is a digital modulation technique in which carrier signal is split into several narrowband overlapping subcarrier signals. So here you can see that the entire frequency bandwidth is divided among the narrow subcarrier channels, and all these subcarriers are orthogonal to each other, and at any particular given time only one of the subcarriers is at a peak value and when compared to others. And this OFDM is widely used in 4G wireless communication systems due to its high bitrate transmission, because there are many subcarriers which are implemented which process parallelly. The bitrate transmission is high, and then high bandwidth efficiency and the effectiveness in handling multipath fading and delay. So that is the basic crux of the OFDM system, that is the parallelly processing subcarrier signals. So the OFDM system salient features are: OFDM is a European standard for digital audio broadcasting and digital video broadcasting. OFDM is extensively used in wireless systems nowadays, and through that is wireless LAN and WiMAX, cell phones, etc. OFDM uses close space overlapping of subcarriers, and thus it effectively uses the entire provided available spectrum or the bandwidth. And so we know that any channel is not an ideal channel, and the channels a signal passing through the channel goes through some fading, that is and this fading is very effectively handled with OFDM system, that is resistance and frequency selective fading. This is the general overview of the OFDM system. It divides the high-speed serial data signal into multiple lower speed subsignals, that is the subcarriers which are parallel to each other, and then the pilot signals are inserted into these subcarriers so that to prevent and frequency and phase shift errors. And then modulation is done on these signals. The modulation can be done through binary phase shift queuing, quadrature phase shift queuing, quadrature amplitude modulation, and etc. And then a cyclic prefix is inserted. Zeros are appended, and these are the extra bits which are inserted to prevent the intersymbol interference. And then it is very easy to implement because of the fast Fourier transforms which are readily available in MATLAB, and it is again easier to switch between the time domain and the frequency domain implementation, because the one and other are inversely related to each other, and when we can do fast Fourier transforms, and inverse fast Fourier transform is as easier, so it is very easy to implement. This is the basic general overview, and then we will now move on to the OFDM system architecture. So this is the block diagram of the OFDM system. Here binary data is being sent, and then mapping and modulation is done over here, and then the data is again converted into parallel sub channels. Here it is converted into parallel sub channels, and the pilots are inserted over here. These pilots will be responsible for channel estimation, and these give the basic idea of these form the basic idea of the channel estimation technique, and then it is passed through the signal is passed through IDFT, inverse discrete Fourier transform signal block, and then a guard is inserted. Here the guard is the cyclic prefix which is inserted to prevent intercarrier interference and intersymbol interference, and then it is converted to parallel to serial data, and it is again given to the channel. Here in the channel, absolute white Gaussian noise is added, because in ideal real-time scenario, every channel has some kind of noise associated with it, and here to emulate that, we add a noise, AWGN noise over here, and then convert the serial data into parallel data. Then the cyclic prefix is moved over here, and the discrete, here the frequency domain signal was here converted into a time domain signal, and here at the discrete Fourier transform, again the time domain signal is then converted into frequency domain signal. And here we will again, with the pilot insertion, we'll get those pilots, and then we'll estimate the channel, and then it passes through the parallel to serial block, and then demapping and demodulation is done, and output data is estimated. So this is the OFDM system architecture, and this is the mathematical model in input to time domain. So inverse discrete Fourier transform, and here the insertion of the guard, and this is the convolution with the channel and the guard removal, then output frequency domain. This is the output frequency domain, and this is the final output. Here you can see H of k is the channel, I of k is the intercarrier interference, and W of k is absolute white Gaussian noise. And here this mathematical represents the estimated channel. H of k gives the estimated channel. So this is the mathematical model. Now we'll move on to the OFDM system model. Generally, the pilot symbols are multiplexed into an OFDM symbol in frequency domain. So they are multiplexed in frequency domain. In addition, the power allocation of data and pilot symbols are given here. So here the power and data and pilot symbols are given. So the total power, so rho is the total power, and beta is the power allocation factor. So the power and the data allocation is given over here. And then the OFDM system model. If the system is perfectly synchronized, the cyclic prefix is added and removed appropriately, then the system is considered to be free of intercarrier interference and intersymbol interference. So as a result, the ith received OFDM symbol after EFT can be expressed as R of I is equals to delta X of I W of I, where delta is an n cross n diagonal channel matrix with the kth element standing for the channel frequency response of the kth subcarrier, and W is the complex white Gaussian noise vector with covariance matrix. So this is the covariance matrix. And now we'll move on to the channel estimation technique in OFDM. Channel estimation is needed in coherent OFDM receivers to compensate for the frequency selective channel and to perform coherent detection if multiple transmit and receive antennas are used. So this is generally more efficient in multipath fading channels. So, and channel estimation is performed by inserting pilot tones into the subcarriers. This pilot tones insertion is done through two methods, that is the comb type and the block type. Here we see the comb type pilot insertion, in which the part of the subcarriers are always reserved as pilot for each symbol. And then here we see the block type. All the subcarriers are used as pilot in a specific period. So depending upon the implementation, either block type or comb type channel estimations are used. And here we see the least square channel estimation, which is one of the block type channel estimations. So this least square channel estimation is modeled such that the weighted errors between the channel estimation measurements and the model are minimized. So this is the mathematical representation of the channel least square channel estimation, and it is very simple to implement compared to the other channel estimation algorithms. The linear minimum mean square error estimator is again one type of pilot channel estimation method. In this, the LMMSE estimate has about 0 to 5 dB gain in signal to noise ratio over d square channel estimate for the same mean square error values. The main drawback of the LMMSE estimate is its high complexity when compared to the LS algorithm, and this complexity grows exponentially with the observation of samples. And a low rank approximation is applied to the LMMSE squared error estimator, which uses frequency correlations of the channel, and here is the mathematical model representation of the channel. And then the time domain channel estimation, this is the crux of our project, and the overall performance of the OFDM system is improved by using a sliding window model of the channel estimation. Time domain LMMSE estimation, the channel impulse response is estimated at an instant k by applying a linear filter on the received OFDM symbols that corresponds to the time window k. The system with large spacing between the pilot carriers and sliding window is positioned symmetrically with respect to the time instant under consideration. This is one type of a comb pilot insertion method, and we will see how exactly it is implemented through the code. And this is the mathematical model of the time domain LMMSE system. So these are the implementation assumptions which we considered: the usage of cyclic prefix, impulse response of channel shorter than the cyclic prefix, and you have the additive wide Gaussian noise, and the rectangular windowing of the transmitted pulses. So these are some of the simulated parameters which were used. That is the FFT of 64 and the number of carriers, the pilot ratio, cyclic prefix length of 8, and then pilot frequency of 4 kHz, signal constellation BPSK, QPSK. The OFDM system is designed using the above parameters, and various simulation results are separately obtained for quadrature amplitude modulation and modulation through phase shift keying. So these are the simulation results. The simulation results for the BER versus the bit error rate versus signal to noise ratio. Here you can see the channel, the original channel, the estimated channels through LMMSE algorithms, the time domain LMMSE, and the time domain QApps LMMSE. And this is the theoretically obtained values for LS and LMMSE algorithms. Here using the covariance matrix and the smoothing covariance signal and smoothing matrix, TDD LMMSE and TDQFs LMMSE are obtained. So the same results, similar results you find for PSK, that is phase shift keying. And then these are the power profiles which are got through the code and the simulations: the power profile for quadrature amplitude modulation and the power profile for PSK. So these are the pilot insertion matrix which we got through the code and the simulations. So this is for the quadrature amplitude modulation, and this is for phase shift keying. And these are the conclusions which we can draw. From the graphs, we can say that the SNR increases as the symbol error rate decreases. It can also be concluded that the block type estimation, which calculates estimators once per block, is simpler than comb type estimation. Block type channel estimators LS and LMMSE are more suitable for slow fading channels, and comb type channel estimations like TD LMMSE are more appropriate for fast fading channels. LS estimator is less complex compared to LMMSE, and TD LMMSE outperforms other models in terms of BER at high speeds. TD LMMSE eliminates the sliding window effect, and it is almost the same performance at all instants within the period of OFDM symbol. LS and LM provide better performance at low values of signal to noise ratio, whereas TD LMMSE provides better performance at higher SNR values, and also QM modulation provides better channel estimation results when compared to PSK modulation. Now we will see the code for OFDM channel estimation. So here are the parameters which I have told before, and this is the conversion. This is the modulation over here with QM or PSK, and here the data is generated with the random signal, and then the modulation is done here. Serial to parallel converted, and the pilot and data locations are specified, after which the pilot is inserted into the locations, and then inverse discrete Fourier transformation is done, and then the cyclic prefix is added over here, and then the random channel is generated with rand_n, and the absolute white Gaussian noise is added over here, and at the bottom we can see the absolute white Gaussian noise. Here we perform the time domain LMMSE function. I mean, we initialize it and perform the time domain LMMSE. And SNR vector B is from 0 to 40. I'm using two vectors, 0 to 40, and the SNR vector is from 1 to 11. And this is the channel convolution and absolute white Gaussian noise, and the receiver processing, and the time domain LMMSE estimation, and time domain LMMSE ignoring channel covariance and ignoring smoothing matrix. And this is the SNR vector and conversion, remover of side prefix, serial to parallel conversion, and the DFFT, discrete Fourier transform. And then channel estimation is done over here, and then it links to the two other files, which are the functions. And then here the parallel to serial, the demapping and the demodulation is done over here, and then the calculation of the bit error rate, and the graphs are plotted over here. And then the MMSE, the mean measurement of signal error is here, over here, and then least mean and minimum mean signal error over here, and the interpolation is done in this code. And that is it with the channel estimation project. And I hope you like my project and the presentation. Thank you.